In this video, we're going to talk about HTTP and the header package. To begin, we'll start with the World Wide Web. Wikipedia's description of this is really good, so it's worth reading. The World Wide Web is an information system where documents and other web resources are identified by Uniform Resource Locators, URLs, which may be interlinked by hypertext and are accessible over the Internet. The resources of the World Wide Web are transferred via the Hypertext Transfer Protocol, HTTP, and may be accessed by users by a software application called a web browser and are published by a software application called a web server. Let's break this apart. First, URLs. We'll talk a lot about URLs in the next slide, so we'll skip them for now. Second, hypertext. Hypertext is interactive text to a different web resource. So usually we see this in blue and it's underlined and we can click on it. That's what you should be thinking when you think of hypertext. This was originally via HTTP methods, but now we see this with JavaScript and all sorts of other things. The Internet. The Internet is just a global network of networks. It's an enormous network of devices, and they all use this Internet protocol suite. So it all uses TCP/IP, just like we've previously discussed. Next, HTTP. So that's going to be an application layer protocol, and it's going to be the main communication protocol that we're actually using when we use the World Wide Web. 5. Browser or a web browser. This is the application that you have on your machine, the client application. It's going to form requests, it's going to receive responses, and then it's going to display the results. Various common web browsers in practice, of course, are things like Chrome, Firefox, Safari, Edge, Opera, and DuckDuckGo, and so on. These are all very common web browsers, and you're undoubtedly familiar with them. Lastly, web server, which you're probably less familiar with. So a web server is just a software application, so it's a program on a computer, and it's going to listen and it's going to respond to requests. So it just sits there all day listening for requests to come in, and then it does something with those requests, it processes them, and then it returns some response to the user. Sometimes when we're referring to a server, we're referring to a big piece of hardware that is actually running that software. So you may hear both come up, just don't get confused. It's usually pretty easy to distinguish. Now, while you're familiar with common web browsers, you're probably not as familiar with web servers. The most common web server out there today, just by a hair, is called Nginx. It's a relatively new web server. A little bit older is Apache, which you probably have heard of. Both of those are open source software and have relatively free licenses. Another common web server is Microsoft's IIS, or Internet Information Services. This is a Windows Server product, and unless you're working in IT, you're probably not going to come across it directly. Very commonly in this area, you will hear people refer to the so-called LAMP stack. In software engineering, when anybody refers to a stack, they're referring to several pieces of software that are bundled together to solve a particular problem. In this case, it's making a website. So the LAMP stack is referring to a person running a Linux operating system, an Apache web server on that Linux-based operating system. They're using MySQL for their database. That's where they're storing all the information for their website. And then traditionally, they're using PHP as a scripting language to code things about that website. However, it's also common to see Perl and nowadays Python in this process. Since the advent and since the increasing popularity of Nginx, you're now seeing a lot of so-called LIMP stacks. It's the same thing as a LAMP stack, but it's running Nginx instead of Apache. Nginx is a little bit newer, has a little bit better features, particularly for things like load balancing, but it's a little bit more challenging to set up at the beginning. Onto URLs. URLs, or Uniform Resource Locators, are going to be addresses that enable clients to easily refer to the location of resources on the World Wide Web, and to some extent communicate with web servers. We'll talk about that in just another minute. Now, the URLs may also identify things like databases and so on, and we'll see that actually in a different lecture. URLs usually identify the computer on which the resource is held, i.e. where the web server is, and the location actually on that computer. Occasionally, you'll see the acronym URI used. That stands for Uniform Resource Identifier, but we won't make a distinction between these. URLs typically also contain some networking information, although nowadays this is usually assumed by web browsers, so you won't always see it there. A standard URL may look something like this: http://www.example.com:80. The HTTP on the front is saying the protocol that's being used. Notice the / is just saying, hey, here's where the end of the protocol is, and here's where the next piece of the URL begins. Then we see what's called the Fully Qualified Domain Name, or FQDN. The Fully Qualified Domain Name is constituted of three parts. The first, the so-called host, that's the www. That's an individual computer on a particular domain. Second, the secondary domain, that in this case, that's example. And then lastly, the so-called top-level domain, that's the .com. These are actually signifying information kind of in reverse scale of granularity. So www, that's the most specific host on the example.com domain. Okay, com itself is the top level domain. So kind of reading right to left, you're going from very general to very specific. Now, when you see the www there, that's actually referring to a computer on which the web server is running. But it doesn't need to be called www. That's just a convention here. In fact, nowadays it's common not to see a host name at all and to use a so-called naked domain. In this case, the naked domain would just be example.com. And in other cases, it's common to see other hosts. For example, if it's actually an FTP host, maybe it's ftp.example.com. So there's lots of different ways we can do this. The :80, I'm assuming you've never seen before, that's actually referring to the port number on the host computer. Here, the port number is 80 because the protocol is HTTP. But if it were HTTPS, it would be 443 and other ports according to other protocols following the general convention. Web browsers will usually infer the port from the protocol being used, and the protocol is typically HTTPS in modern web browsers. So it's common for web browsers to not need the HTTP on front or the port 80 on the end because it's actually going to use HTTPS and 443, but it's just going to assume that since you're on a web browser. Now, URLs can also be used to communicate with web servers in a kind of limited capacity. This is through something called a Web Application Programming Interface, or a Web API. And it's really just going to dictate how your computer makes requests to the server, and then how that server is going to speak back to you, okay? Here's a way you can think about this. If plugs and ports on switches and routers are called interfaces, APIs are like plugs and ports into software, and the software is going to be the kind of server-side service that you want to access. So the API is going to just say like how you do that. Using an API, you can do more than just request static resources from a computer. You can do things like tell the computer to do computations, or you can update a database, or you can do all sorts of things using a web API. Nowadays, most web APIs are so-called RESTful web APIs. So whenever you see REST or RESTful, you should be thinking these are the standard APIs that are used these days. And you can learn more about that by either going to the Wikipedia article or going to programmableweb.com. Now, the responses are going to come to the client via HTTP or, as I said, HTTPS, and they're commonly going to be in HTML, XML, or JSON. Okay, those are going to be like the file formats that you get back. We'll talk about JSON in just a minute, and we'll talk about HTML and XML when we talk about rvest. Now, with this kind of increasing level of complexity, our URLs also get a little bit more complicated. So now we have a little bit longer URL. We have first the path of the data. So notice that that looks like a path on a normal Linux-based or Linux-alike machine, right? Forward slashes and so on, referring to a particular location on the computer. By web developers, these are usually referred to as resources. Following that is a question mark, and the question mark initiates what we call the query. The query is a sequence of key value pairs that are identified with equal signs and joined together with the ampersand. So this is kind of like calling a function where the argument A is equal to 1 and the argument B is equal to 2. But it has to say that in a string. That's how you actually embed these things in URLs. Lastly, the hashtag followed by the ID. This is going to denote a kind of session labeled fragment ID and usually is not going to be of interest to us. As an example of what something like this may look like, here is actually a real-life URL pulling some information about Waco, Texas from Google Maps. So notice that on the far left there, we're working over HTTPS, so it's an encrypted protocol. We're referring to maps.googleapis.com, that's the fully qualified domain name. The path or the resources that we want is under Maps API geocode JSON. JSON is actually going to be the format that we're going to get this back in. Query address equals Waco something something Texas. That something something is actually URL encoding, which is just making that string safe to go out on the internet to then be resolved into an IP address through the DNS that we'll talk about when we talk about rvest. So let's think a little bit more about that JSON there. JSON, or .json, that's the file extension, stands for JavaScript Object Notation, and it's a file format, a data file format that is human readable text that consists of key value pairs, think something like a named list, and it can have array types as well. So for example, here's an example of some data that's encoded in JSON. So notice first name, John, last name, Smith. We can read this even though we've never seen JSON before. Address, street address, city, state, and so on. So you read this and it looks very much like a named list. And in fact, that's usually how we convert it in R. So we use the JSON-like package, we use read JSON, and there we go. It converts it right into a named list. and all of the same information. Now we may want to do some other little parsing on it. For example, we may want to change the phone numbers to be actual numbers, or we may want to add a street number and pull off that 21, and maybe that's an integer or something like that. But in general, this is how we're looking at JSON. Most major websites have APIs that will serve data to you in the form of JSON. So before we were looking at Google Maps, we saw that URL for Google Maps information about Waco, Texas. If you actually type that into your web browser, this is what you get. So it looks just like textual data. That textual data can then be pulled into R, can be parsed, and can be analyzed, or added to a larger data set. In a setting with spatial data like this, usually that process is referred to as geocoding. So you'll give the service an address, and it will give you back information about that address. What is its county? What's its latitude, longitude? Things like that. There are tons of web APIs out there. So obviously, maps and spatial data have web APIs. Weather and climate data, for example, NOAA and other government resources will have APIs. Financial data and economic data, things like Google Finance or Yahoo Finance. You could pull down stock data or other kinds of financial data. Social media data, Twitter, Facebook, Instagram data, all of this can be pulled down. Even things like sports data, which is updated frequently. So these are kind of common repositories of data, and the way that you as a data scientist will access them is usually through a web API. It's usually not you go to some website, you click on some file and it downloads it and then you read it in. Although occasionally it is. More often you're going to use a web API to pull data off of the internet. Now these web APIs, occasionally they will be totally free and totally open. More often they will require accounts, but may be free in a gratis sense. In other words, you'll have to make an account, but you won't actually have to pay money for that account, kind of like Google's search engine. In software circles, that model is usually referred to as gratis, the idea being that the company that actually provides the service is getting paid in some other way, usually having to deal with knowing things about you and selling the things about you to some other service. If this is the case, then the service itself needs to know about you if you have an account. So HTTP requests need to have authenticating information, and there are different places in which that can actually go. Associated with this, you'll hear terms like OAuth or access tokens or two-factor. Things like that, they're all associated with this authentication process and can be more or less challenging to actually set up. In the Google Maps example, you may see here at the very end of the URL, there's a kind of cut off part of the URL starting with key. Okay, it's one of the keys of the key value pairs, and this is actually going to communicate my private API key for Google Maps. And if I shared that with you, you would be able to use it as well. And in fact, you could, in some ways, charge money on my credit card by using a lot of those resources because you actually pay for a number of queries that are made to its servers. And it knows that it's you because you're using your API key. So these are secret keys and you don't share them. Now more into HTTP. HTTP operates using a small collection of methods. These are all in caps and they are case sensitive. Header functions follow the same naming conventions to try to stick as closely as possible to the underlying HTTP verbs that they're actually using. Here are the methods that header is actually going to support. So a get method. Get is going to be used for querying a web server for data at some URL. So you'll say get from a particular URL, and it's going to ask that web server for that particular resource. Usually, if you're just browsing the internet, that resource is an HTML page. But if you're trying to download something, it may be something like an RData file, or a CSV file, or a JPEG, so something significantly larger. So you can get all sorts of things from web servers. Head is exactly like get, but it doesn't have the body associated with it. We'll talk about that body in just a minute. The next two most important verbs that you really need to know are post and put. And they do very, very similar things, and it can be confusing and very API dependent on which one you should use in which particular circumstance. The idea for both of them is that instead of pulling information down from the web server, you're putting information back up on the server. This may be something as simple as you're filling out a web form for an address, or your user ID and password, but it could be much more complicated than that as well. Delete, patch, do pretty obvious things. Retry is actually going to take a verb like get or post, and then it's just going to keep doing it over and over and over until the web server says that it has been successful in actually doing that particular action. So retry and browse are not HTTP verbs. They are in header and they look like verbs, but they do something that is verb-like. Retry, again, just hits a server several times in a nice way to try to accomplish a particular task. Browse is actually going to open up your system's web browser on your computer. So if I use it on my computer, it's going to open up Safari. If you use it on yours, maybe Chrome or Firefox or something like that. Now, how do these things actually work? They work through sending what's called HTTP messages. These are requests that are actually just plain text files that encode what one machine wants the other machine to do. They're constituted of three components. First, there's an initial line that communicates the basic protocol information, such as the HTTP version number. Next is headers. This is optional. It's a number of key value pairs that are going to kind of characterize the request. For example, if you want to get JSON back from the server, you can tell it there, hey, I want the output to be in JSON. Okay? It may also contain authentication information about who you are trying to access that particular web service. Or that information could be contained in the body. So there's some flexibility here, and it's going to be API dependent. The third thing is this body. It too is optional, and it's going to contain data. The data could be the response data. You ask a server for some data, it sends you back the data. That data is actually part of the body of that HTTP message, even though your request came simply as an initial line with some headers. The body could also contain data to be uploaded, like a blog post, or it could contain authentication information to actually authenticate yourself to the web server. So structurally, these things are going to look like this. The initial line, the headers, there's a blank line, and then there's going to be the body of that message. Now, over the next several slides, I'm going to illustrate this with this particular web page, httpbin.org/get. This is a common web page to illustrate various HTTP things with. If I were to just type this into Chrome, this is what I would get. So obviously I'm getting some JavaScript object notation back that's containing that HTTP information. If I want to do this in R, I'm going to use hitter's get verb. So get, I give it the URL, and in this case, I say verbose. That verbose is going to tell the verb, here get, to tell me the messages that it's sending out and that it receives from the web server. Okay, that's everything here in orange, and you'll see that there are some arrows to the right. Those are saying that that's the information you send out, and then the arrows to the left, that's the message that you receive back from the server. If I colorize these, it looks like this, and I can kind of break this up in the same way that we saw before. So here's the message to the server. Here's the message we received back. So the first one in both cases says, hey, we're talking in HTTP version 1.1, okay? You'll see the 200 OK there in the response. That's saying that everything went well. We'll come back to that in just a minute. Then you see things like the date, should we keep the connection alive, all of this kind of stuff, okay? So these are just very typical things to see in HTTP messages. The body of the response is not shown. That is actually going to be kicked back. You can actually see it's kind of starting, and then it goes off the page below. If I store this, I'll store this as something called response, and now I turn verbose off, so you can kind of see the rest of the things there. So you see things like there's the header information, there's the origin, i.e. that's my IP address, and so on. If I look at the structure of this, it's a list of length 10. It's a named list, so this is a very familiar object in the R language, and it's based on, exactly what you would think. It has the URL, the status code, headers, cookies. We haven't talked about cookies. It's going to allow you to communicate other things like preferences and stuff to the web server. Content, the date at which this was done, and then lastly, there's that handle. The handle is a pointer to a curl object, which usually won't matter to us, okay? Let's talk a little bit more about statuses. HTTP has a number of predefined status codes that are communicated in numbers that are associated with English phrases that say something about how the web server considered your response. An HTTP status of 200 means okay, which is everything went to plan, everything worked exactly as you would expect. If you see 404, and you have probably seen these on a web page before, you get a not found error. This is when you're asking the web server for something, but it actually doesn't have the thing that you're asking for. Generally, things in the 400 range are bad. So a 400 itself is a bad request. This means that you are communicating something to the web server, but the web server, for whatever reason, didn't like what you were communicating. It was an improper way to communicate it or something like that. And so it's not going to respond to you. You also have weird things like 418, I'm a teapot. So there's some IT humor that's kind of baked into these HTTP statuses. Hitter will allow you to check these codes with HTTP status, or you could just pull it straight from the response itself. Straight from the response, you have things like this. The status code was one of the named members of the response, and we get 200 back, and we just need to know that 200 is, okay, everything is just fine. Otherwise, you can use the HTTP status function, and it's actually going to parse that for us a bit, okay? When you're making functions, what you may want to do is you may want to look at that status and then warn the user or throw an error yourself, depending on what the status was. And so there are functions that actually do that. Warn for a status, stop for status. You can check the HTTP response header information just with the headers function. Of course, it's going to give you back a named list, just like the response itself. And this may be more or less useful just depending on your application, though I typically don't find it so useful. It can certainly say things about the server. Now, of course, the reason why we're querying web servers in the first place is because we want information from them. We can get the information back using the content function. So response piped into content raw is actually going to give us the raw bytes of the information that the server sent back to us. Obviously, that's not particularly legible, so we can do things like ask for the text content of the response. Notice that this is going to come back as a formatted string. If we want to see what it looks like, we would need to use something like cat or write lines on it. So this is the actual response that we're getting from that server, and it's much more human readable now because HTTP messages are human readable. If you want to actually convert the response from the server into something that's useful, if you want to actually parse it, you could use string processing on the text content that the server gives you back, or you could use content parse. Content parse is going to use one of a number of methods that we'll see in just a minute to try to actually convert the response from the server into an object in R that is more or less usable. Okay? As an example of using these things, in the past we've seen web scraping using just basic read lines and our string processing. We could actually supplant that now that we know about HTTP request by using a GET request, pulling out the text, and then using string processing to pull out everything following a particular pattern. So we're seeing more and more sophisticated ways of using R to scrape data off of the internet. One thing that's really useful with httr is actually downloading files programmatically. By default, when you run GET, it will query a web server, the web server will respond, and the information of the response will be actually stored in your computer's memory. If you want to save that to disk, you need to use the write disk function inside of the GET query. This is really important for big files because you don't want to have to download the file over and over again every time you use the GET expression. For example, every time you're compiling a document or something like that. You really want to save the file to your disk and then you can just pull it from disk. That would look something like this. So you say GET, you give it a URL, and then you say write disk in the file name that you want to write. So here you see the response. It's coming from this particular web server. In other words, the web server that I gave it the URL before was an alias for a different web server. And so it kicks it to a different web server, and then that's where the actual resource is found. It downloads it, has its date, the status is 200, everything worked perfectly, and it saved it on disk to cv.pdf. If I wanted to actually see this, of course I could open it on my computer, or I could type in something like file show, and it will actually open up my default PDF viewer. Now the last thing that I want to talk about in terms of httr is actually another package called Plumber. Plumber is going to allow you to spin up a web server with an R instance backend that's pre-provisioned with functions that are accessible as HTTP endpoints. If that sounds confusing, it's actually not. You just need to see it in action. The idea here is that you want users to be able to simply type in a URL in a web browser or at a command line or something like that, query your web server, and in querying the web server, they're actually just evaluating an R function call. Okay? So it's not that bad. Here's how this works. You'll have a file that's just a simple R script file. The R script file will be formatted in a particular way that the Plumber package understands. Let's start with the things that we do know. We do know what functions are in the R language, so we understand those things perfectly. The first one is a function. It accepts no arguments. It generates some normal numbers and just makes a histogram of them. The output would be a plot. The second one accepts two numbers, and it just adds them together and returns another number. So really simple, right? The Plumber markup is going to ask for a hashtag followed by the asterisk symbol. That's how the Plumber functions are going to know stuff about the functions that you're defining. Notice that you never actually named those functions because you're not going to be using them directly. You're going to be using them as a Web API resource. So if you access the resource called /plot, it's going to evaluate this function right here. If you access the web resource called /sum, it's going to evaluate that function right there. Now, notice that the second one, the sum, actually has parameters associated with it, right? You need to give it those parameters to actually do the evaluation. We'll see how Plumber deals with that in a second, but of course that's very different than the first one. Notice also that the first one is accessed through a HTTP GET method, whereas the second one is going to be accessed through a POST method. In the first one, you just needed to say, hey, give me a plot. I don't need to give you anything for it. Now, once you've saved this 15-line R script file to your disk, you can use Plumber to actually make the web API for you. So you say, plumb that particular file. It's saying create a resource that then can be launched to be a web server that's going to have the endpoints that we previously defined. Now you're actually going to run that particular web API, and notice that it says it's starting server to listen on port 8000. So all of these kinds of things are going to have conventional ports associated with them. We know what that means now. So it's port 8000, and it's going to run the Swagger UI at http://127.0.0.1, that's localhost, that's yourself, on port 8000. I will mention in passing that this markup over here, like these hashtags followed by the asterisk, those are very similar to what's called Roxygen documentation for R packages. But in Roxygen, you use a hashtag followed by a single apostrophe, so it's slightly different. Now, when you run this, you're first going to get something in RStudio that looks like this over here. That's that Swagger screen, and it's going to allow you to kind of play around with the API in a really convenient way. So you don't actually have to query it manually from the command line or something like that. You can literally just start clicking around to create HTTP queries and to see what the server does. Notice on the right-hand side, I have actually just gone to a browser. I typed in localhost, that's 127.0.0.1, :8000, that's the port that it's listening on, and then I refer to the plot resource. When you're using a web browser, web browsers are by default going to submit GET requests to the web server, which is good because we know in this case, the plot resource accepts GET requests, right? So what did it do? It generated those normal variates, it made a histogram of them, and then it returned that plot to you as a .png file. That's just what it does by default. Using the sum function is a little bit more challenging because we can't access it with a GET request through a web browser. So now we're going to use the post method in httr, which is a post HTTP request. And notice here that the URL says, use the sum resource, and by the way, here are those parameters that are associated with that particular resource. B is 2 and A is 1. Of course, the return value is going to be the sum of those two things, and I can access that by getting the content of the response. I'll also note in passing that we could have done this from the command line using the curl library, which is a really common way to download things or, in general, make HTTP requests from the command line. Now, in the real world, Plumber will almost certainly not be on your own machine. You usually don't need to serve yourself something, although occasionally you do actually do this. It's a standard way to do things. Moreover, without changing some settings in your router, you usually can't be found behind your router because of network address translation. So internally, your computer, which is running the web server, will be discoverable by other people internally on your network if you're on a computer that's outside of your network. So maybe your web server computer is at Baylor and you're working from your house. That's going to be inaccessible to you because it's going to be behind the university's firewall and its router, which is undoubtedly going to block all of this traffic. Moreover, remember that your IP address is constantly changing. Whenever you unplug your computer and plug it back into the network, in most routers and most network setups, you're going to get a new IP address. It's going to be from a large block of IP addresses, but it's going to be a different one. So it's more challenging to say which computer do you actually want R to talk to. There are ways to deal with this problem, but the last thing I'll say is that there are security concerns associated with them. For example, you could just say, well, router, every time you get a external HTTP request, just pass it on through to this other computer. And that is done very commonly for all sorts of things. But it also brings with it some security concerns. If you're letting through things into your home network or into your internal network, you're exposing yourself to the outside world, which can be a dangerous thing. Real-world use of Plumber will almost always use remote hosting. Plumber itself facilitates hosting using DigitalOcean, which is a cloud platform. Alternatively, you can use things like Amazon Web Services, Google Cloud Platform, Azure, or IBM Cloud. Moreover, it makes virtualization easy because Docker images are available from Plumber's website that you can just pull down and then launch a Docker container that contains all of the R code and all of the plumbing inside that it needs to host a web API. So that's HTTP, httr, and a few other cool things.